Hello. In the first assignment that you did using ASE, we ran molecular dynamics and calculated properties of materials by taking ensemble averages. If you are studying the behavior of liquids or proteins, this is often the only approach that is available to you. If you are studying a solid, however, there is another, less computationally expensive approach that you can take when it comes to calculating the properties. Furthermore, this approach gives you partial access to the nuclear quantum effects that are missing when you compute properties using classical molecular dynamics simulation. In this video, we are thus going to examine this other approach for studying the behavior of solid-state systems. This approach is based on assuming that the system can be thought of as a collection of harmonic oscillators. Let's start this process of understanding this alternative approach by looking at something simple, namely the dynamics of a single particle that has a potential that depends on only one position coordinate. In other words, let's think again about the sort of systems that we looked at in the second of the assignments for the MTH 4332 module, the assignment where we introduced the topic of molecular dynamics. Notice that we can express whatever wacky potential we dreamed up for V of x using the Taylor series. In other words, all the potentials that you used for V of x in the second assignment can be estimated by using the Taylor series shown here. In other words, we can use this Taylor series instead of using the particular expression for V of x that you employed in your report. As you hopefully know, the Taylor series has to be expanded around a point. This is the point x0 in this expression. When we use the Taylor series in the way that I'm going to describe in this video, we will choose x0 to be the location of a minimum in the potential V of x. The V of x0 here is thus the energy the system has when it is at in the minimum. Better still, because we are at a minimum, the first derivative of v with respect to x at x0 is equal to 0. This whole second term in the Taylor series thus goes to 0. We divide the remaining terms in this expression into two parts. We call the parts in delta squared the harmonic terms, and then everything else, other than the V of x0, the anharmonic terms. Notice that when delta is small, delta squared over 2 will be larger than delta cubed over 3 factorial and delta to the 4 over 4 factorial. This realization is important as it tells us that if delta is small, the harmonic terms will be much larger than the anharmonic terms. If you're willing to assume that delta is always small, we can thus neglect the anharmonic terms in this expression. As you hopefully saw when you completed the Block 2 assignment, this assumption that delta is small is reasonable when the temperature is low. When the temperature is low, the system does not move far from its minimum energy position. For low temperature, it is thus reasonable to assume that we can calculate the potential energy by only computing the harmonic terms in the Taylor expansion for V of x. When the temperature is small, these anharmonic terms and their contribution is very small. The fact that we can use the Taylor series to approximate the potential, as I have described here, is enormously useful. It basically converts the potential energy expression into the potential energy expression for a harmonic oscillator. The reason this works is that the second derivative evaluated at x0 here is just the number. The whole potential thus reduces to c, the energy at the minimum, plus a half k delta squared. This is the Hamiltonian for a harmonic oscillator, and as you have seen, we can get a partition function for the harmonic oscillator using both classical and quantum mechanics. The quantum mechanical expression for the partition function of a harmonic oscillator is given by this expression here. Consequently, because of this Taylor series expansion that we can use for the potential, we can approximate any potential using the expression for a harmonic oscillator. We have in fact been using the classical analogue of this idea throughout the module. It is the reason for the equal partition theorem that we have used to determine average energies and heat capacities repeatedly. If it helps, what I am doing here is reformulating the equipartition theorem in a way that recognizes the fundamentally quantum nature of the atoms that materials are composed of. I am possibly getting ahead of myself here by telling you that, though, as so far we have only showed that any potential that is a function of a single position coordinate can be approximated as a harmonic oscillator. We really need to generalize this insight and show how the same idea can be used with potentials of functions that are functions of more than one position coordinate. Without further ado then, let's suppose that we have a potential that depends on two positions coordinates x and y. We can write a Taylor series expansion for this function as shown here. As we did in the 1D case, we will assume that we are expanding the Taylor series around a point where there is a minimum in the potential energy. In other words, we will assume that there is a minimum for V at the point x0, y0. As has appeared, if this is the case, then the partial derivatives of V with respect to x and y at x0 and y0 are both 0. The second term in our Taylor series can thus be disregarded. Furthermore, if we can write V as a function of x and y only, this implies that any integral around a closed path should be 0. In other words, V is an exact differential. As this is true, the off-diagonal elements of this matrix of second derivatives must be equal. In other words, the matrix of second derivatives must be symmetric. Once we recognize that we can use matrices and vectors to write out a two-dimensional analogue of the one-dimensional Taylor series, as we have done at the top of the slide, it is easy to see how we can write a Taylor series to expand a function of n coordinates, as shown here. In this expression, V of x1', x2' is the value of the potential at the minimum, which is located at x1', x2', etc. The x1', x2' are used to denote the coordinates at the minimum. Delta is then a vector that tells us how to move from the minimum in the potential to the point of interest, where we are evaluating the function. The vector of first partial derivatives of V with respect to each of the coordinates is the negative of the force evaluated at the minimum. As we are at a minimum, every component of this vector is 0. We can thus disregard this second term again. We can thus approximate V at any point using the expression with two terms that has only the expression with two terms that is shown here. The more interesting second term in this expression contains the matrix of second derivatives of the potentials. This matrix is sometimes known as the Hessian matrix, and it must be symmetric because, as we saw in the 2D case, the integral of V around any closed path has to be 0. Because it is square and symmetric, we can diagonalize this matrix and replace it with the following product of three matrices. The matrix V here contains the n eigenvectors of H, while the matrix lambda is a diagonal matrix that has the eigenvalues of H on its diagonal. V transpose is obviously the transpose of V. When we replace H with this decomposition, we thus arrive at the expression shown at the top of the slide here. Furthermore, remember that we are expanding around a minimum in the potential, so F is 0. Let's pause for a moment and think about what this expression is telling us by sketching what this function v would look like if it depended on only two positions. An example of a 2D potential that might be of interest is shown here. The coordinates x1 and x2 that enter the expression for this potential tell us how far we need to move along the x and along the y-axis shown here. The directions we have chosen to project on to get x1 and x2 are arbitrary, however. If we had wanted, we could have written v as a function of a different pair of orthogonal vectors. For instance, we could have written v as a function of the projection on the coordinates of the vectors e1 and e2 that I am showing here. In other words, you could have used a different basis set to describe your position in this vector space. In modules on linear algebra, you will have learned that we can transform from one basis set to another by evaluating linear combinations such as those shown here. In other words, the projection of the vector of interest on the vectors e1 and e2 in the diagram can be calculated from their projections on the vectors that I have labelled x1 and x2. You will also have learned that you can write this pair of linear equations using matrix notation as shown here. Notice that when we do this coordinate transform, we are multiplying a 2 by 2 matrix by a vector with 2 coordinate. What emerges from this procedure is a two-dimensional vector. By the same token, if we had an n-dimensional function, we would have an n-dimensional vector here, and an n by n square matrix would be used to transform from one basis set to the other. I have reminded you of all this because we are doing this business of multiplying an n-dimensional vector by an n by n square matrix here in the Taylor series that we wrote at the top of the slide. We can thus replace V transpose times delta with a vector that tells us the projections on a different basis set of vectors. Notice furthermore that delta transpose times V is the transpose of V transpose times delta. We can thus rewrite the Taylor series at the top of the slide as shown here. In doing this, we have replaced the x1, x2 and so on with e1, e2 and so on, so as to indicate that we are using the eigenvectors of the matrix of second derivatives of the function as a basis set. Our function is thus written in terms of the projections on these eigenvectors here. Furthermore, the first derivatives in the vector f and the second derivatives in lambda are derivatives with respect to the projections on the eigenvalues. For f, this actually makes no difference. Because we're still expanding starting from a minimum, the derivatives of v with respect to e1, e2 and so on are still 0. To remind you, chi in these expressions is the projection of the vector delta in the expression onto the various eigenvectors. In other words, it is equal to V transpose delta in the top expression. Lambda is thus the diagonal matrix that contains the eigenvalues. If we have a two-dimensional function, v of x1, x2, we can thus write out all the matrices in this expression as shown here. Let's now multiply out the matrices and vectors in the second term. If we multiply the matrix by the column vector, we get the following column vector. When we then multiply this by the row vector, what emerges is the following sum of 3 terms. The second derivatives in this expression are the values that these second derivatives take when they are evaluated at the minimum in the potential. These derivatives are just scalar numbers though. We can thus replace the second derivatives in this expression with the scalar valued constants k1 and K2 as shown here. Notice that what is left is just the sum of 1D harmonic oscillators. Furthermore, there are no cross terms within this expression that couple the displacements of the different coordinates. This recognition is important as it makes evaluating the partition function easy. When we evaluate the partition function, we will take the exponential of this sum of terms. Obviously, any exponential of a sum can be rewritten as a product of exponentials. We will thus write the partition function for a potential that consists of a sum of harmonic oscillators as a product of partition functions for a series of 1D harmonic oscillators, as shown here. In other words, if we are willing to assume that our n-dimensional potential contains only harmonic terms, we can evaluate the partition function for it analytically. The techniques of Monte Carlo and molecular dynamics that you've learned for this module are only necessary if you want to study the effect that anharmonic potentials have. To reiterate, however, if the potential is harmonic, then the problem is solved regardless of whether the number of position coordinates that appear inside the expression for the potential is 1, 20, or even 1,000,000. In all these cases, the partition function is just a product of partition functions for 1D harmonic oscillators. The alternative to molecular dynamics that I advertised at the start of this video works by assuming that the anharmonic terms in the potential only make a small contribution to the overall potential energy. In fact, the contribution of these terms is assumed to be so small that we can set it to 0 and we can use the expression at the bottom of this slide for the partition function to arrive at an analytic expression for the partition function of the material. Once we have this analytic expression for the partition function, we can then derive values for the ensemble averages that might interest us by taking suitable derivatives of this partition function, which is just a partition function for a product of harmonic oscillators. In the exercises, I'm going to show you how you can use ASE to implement this alternative analytic procedure for extracting ensemble averages. The first step in doing this type of calculation will involve setting up an initial structure for the system and telling ASE how the energy of microstates are to be evaluated. These two steps are done in the same way as that they are performed when we do an MD simulation. In other words, you use the command shown at the top of the slide, which now should be familiar. After the initial structure has been set and the potential has been set, you run a minimization to find a local minimum in the potential energy. In other words, you follow the forces acting on the system, which should eventually take you to a minimum in the energy. There are various algorithms for minimizing the energy, and many of these algorithms are implemented in ASE. In this course, we will be using the BFGS minimizer, which is called and run as shown here. This function moves the positions of the atoms in the ASE atoms object that is passed to it to a minimum in the potential. Once you have done the minimization, you can then calculate the matrix of second derivatives at the minimum. In ASE, this calculations of the second derivatives can be done numerically by using the commands shown here. Once the matrix of second derivatives is computed, you can then diagonalize it. You can use numpy in Python to diagonalize square matrices. The commands you need to do this diagonalization step are shown here. It's a single line. The final step is then to take the square roots of the eigenvalues that you obtain by diagonalizing the Hessian. These square roots of the eigenvalues are the quantities that will enter all the equations for the ensemble averages that you'll use to calculate, to complete the assignment. To take these square roots, you do the following, obviously. One of the first parts of this assignment asks you to draw a histogram using the data in the NumPy array of frequencies that you arrive at by using the procedure that is outlined on this slide. If you are given a NumPy array, you should now know enough Python programming to calculate a histogram from that data. Frequencies here is, after all, just a 1D NumPy array. You can do to this 1D NumPy array what you could do to any other 1D NumPy array. For example, the commands shown here will calculate the maximum and minimum frequency. Notice that because you are at a minimum in the potential, all these frequencies should be real positive numbers. If any of the frequencies are imaginary, then the minimization algorithm has not managed to find a true minimum in the potential energy. And that is about all I wanted to tell you about the alternative to molecular dynamics that you will be using for the first part of the final assignment. As I said at the start, this method works pretty well for solids, as it is okay to assume that the potential is purely harmonic when the system is in the solid states. It breaks down entirely when you are studying liquids, however, as anharmonicity starts to play a big role. Learning to run molecular dynamics simulations has thus not been a complete waste of your time, as although this works in some cases, molecular dynamics is definitely necessary in many other cases. Thank you for your attention, and as always, good luck with the exercises.